So let us begin that. The only scary thing about this procedure is this formula. The implementation of the formula is not difficult. Most difficult part in this formula, if you look at the formula, the most difficult part in this formula is to establish the T matrix. From writing down the hypothesis, you will know how to write down the hypothesis. I will give you the condition to test. From that condition, you need to write a T matrix. That's the most critical part of this one. Once you are done with writing down the T matrix, it's just plugging into the formula and getting the final answer for F. So this formula is not something to be worried of. The thing that needs to be worried of is how to develop a T matrix from what needs to be tested. So let us continue with the same example that we have been doing with two predictors. And let us say I have this model yi equals beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon I. Here y is the delivery time, x1 is the delivery volume, and x2 is the distance, I think. X2 is the distance. Now, if I want to test the significance of x1, I can simply use either a t-test or a partial f-test. Both can be used for testing the significance. Some remarks for your interest. If I want to test that beta 2 is more than or equal to 0 against beta 2 is less than 0, can I use a partial f-test? The answer is no. The only option is to use the t-test. There is no one-sided version of f-test. Remember, there is no one-sided version of f-test. The only one-sided test for third chapter is the t-test. Now, if I want to test this hypothesis that beta 2 equals 0 against H1 that beta 2 is not equal to 0, I have two options. I can use the t-test and I can also use the partial f-test, which is the extra sum of squares method. I can use that. It is because the spirit of developing the F statistic is two-sided. The way we develop the F statistic, the spirit behind that one is two-sided, to just check around 0 and not one side of the 0. It cannot be negative. That's the different thing because it's the square quantity. Yeah. Yeah, when you square it, you lose the sign. Yes, true. Somehow it is connected. Now, none of the hypothesis testing procedures that we discussed, three of them, none of them, they allow you to test this. For example, that beta naught minus beta 1 is 2. This is a linear constraint onto the model. If I want you to test this one, none of the procedures will allow you. Or I can give you two conditions. Test this and beta 1 plus 2 beta 2 is 1.2, let's say, against H1. That at least one of the conditions in H1 is wrong. Yes. The constraint is both of them are linear in their linear form. There is no power to the betas. The power of the betas should be 1. Again, this procedure will not allow you to test this beta 1 minus beta naught minus beta 1 square. So the constraints should be linear. Now, to test these constraints, there is one way of testing it using the partial f-test, which means you plug these constraints into the model and get the revised model, which is fairly very long, very long. So the easier way is to use this generalized linear test, f-test. And to do that, you need to convert this H0 and H1 in terms of matrices. You need to convert these hypotheses into following form, which is your H0 should be T beta equals C, and your H1 should be T beta is not equal C. So you have to define the matrix T and vector C in such a way that T beta equals C becomes that. Now I'll tell you the way how can I define my T beta and C in such a way that this first condition will be covered within the T and C. Now tell me, how do we write beta? For this example, we have how many betas? Beta naught, beta 1, and beta 2. So here it is, beta naught, beta 1, beta 2. This is my beta vector, correct? My T matrix will be something like this, and equal to my C vector should be, again, a vector, a column vector. I need to fill this bracket and this bracket in such a way that this product equals C becomes that. One minus 1, 0. Multiply it. What do you get? 1 times beta naught minus 1 times beta 1 plus 0 times beta 2 equals 2. You get the first condition? Write another row for the second condition. For the second condition, 0, because there is no beta naught there. 1, 2 equals 1.2. Now look at these matrices multiplication equals to a vector, and look at those conditions. If I multiply these equals this, do I get exactly that thing? Do I get exactly that thing? So call this thing now as, and call this thing as your C vector, and you're done. You just plug these things into this formula and you will get the F statistic. And then the routine method, just find the p-value or the critical value approach, whatever you want. So let us do this procedure. And before I do this procedure, let us practice one more time. Let's say make T matrix and C vector for another example. Let's say I want to test that beta 2 equals beta 1 equals no, let's call it beta naught, and beta 2 are 0. How do I write T matrix for this one? Yes. 1, 0, minus 1 equals 0. Now multiply this one. What does this give you? This will give you beta naught minus beta 2 equals 0. Is it equivalent to that H naught? It's not. It's not. It is not. This is testing. This is equivalent to saying that beta 1, beta naught equals beta 2, but not equals 0. They are equal to each other. They may be 2, they may be 7, they may be 19, but they are equal to each other, not equal to 0. Let's say if I make it plus, this will become plus, this will become minus, still not equal to 0. Let us try one more time.
Add another column T.
Add another row. in. If you look at your H naught, it's not a one condition. It's not a one condition. These are two conditions, that beta naught is 0 and beta 2 is 0. So you need to write two rows of T matrix. The first row will be 1 0 0 equals 0, and the second row will be network error. Back. Yes. What was the question? Mobile in the pocket. Don't take it out next time. 0 0 1. The second condition, that beta 2 is 0. There are two conditions, beta naught is 0 and beta 2 is 0 in H naught. Look at H naught at the top.
Second one here, B2 is not 0.
It is 0. Multiply it. Multiply the matrices, you will get beta naught plus 0 times beta 1 plus 0 times beta 2 equals 0. This is the first line, which is equivalent to beta naught equals 0. And the second line is 0 times beta naught plus 0 times beta 1 plus 1 times beta 2 equals 0, which is equivalent to beta 2 equals 0. After this,
Why we are changing to this TB equal to?
this is the substitute of what do you call that? Full model and revised model. Because writing it in that form, it's difficult. The proper way is to do that. But even that model comes from this generalized F statistic. If you open this T, put the T, beta, and see everything in this matrix and try to simplify it, you will see you will reach that point. SSR of the full model minus SSR of the reduced model over R. Again?
Should be too long to do this.
This is not long, that is long. This is not long. That one is more long. This one is more formal, more compact. That one is long. If I give you 7 conditions to test, then plugging in the 7 conditions into the model and then simplifying in and getting the reduced model is very, very tough.
So it's common to make like this test, like the difference between the betas equal. Can you give us an example?
I will give you example, but once I test it, I will tell you where is it practical. It's not practical to formalize the hypothesis after fitting the model. The hypothesis comes before getting the data. For example, I fit the model and I get beta 1 had to be 1.2 and I get beta 2 had to be 0.8, and then I start testing that beta 1 plus beta 2 equals 2. No. After seeing this, I should not be testing that beta 1 plus beta 2 is 2. Of course, if I test, I will accept this hypothesis because apparently they are equal to 2, correct? This should not be done after seeing the constants. If you have a real reason to do the test, it will come before the hypothesis that from some studies or for some reasons, the scientist believes that the coefficient attached with the delivery volume and the coefficient attached with the distance, they are related to each other and they are no different. One of them is nothing but the second one plus 1. So it goes the other way, not after fitting the data. It comes from the one who is designing the study, who's the expert of the variables. If he believes that this is true, then we collect the data. Yes, then we collect the data. first the hypothesis comes, then we collect the data, and then we test the hypothesis. If it is true, then we fit the restricted model and not the full model. We go with the restricted one. Okay, let us do this one in Excel. These two conditions. Or one more example. Let's say if I want to test just this hypothesis, beta 2 equals 0. Because I have the p-value for this one. I want to replicate the same p-value using. What if I want to test this one? T will be 0, 0, 1, and C will be 0, correct? Let us do this one because I have the p-value. I have the p-value for this one from the t-test. I have the p-value for this one from partial f-test, and we matched those two and they were equal. And you will see this one will also, if the things go correct, be equal to the one we found there. So I'm expecting the p-value to be 0.000631. So let us do the partial f-test here. No, not the partial f-test. Generalized f-test. The first thing I'm going to do is I'm going to write the t matrix. The t matrix is 0, 0, 1. Correct? And then I write the C vector. C vector has just a 1 row, 1 column, which is 0. Once I wrote it, I'll just put everything into the. Do I have the betas? Beta hat vector, where is it? Here it is, I think. This is beta hat vector. So let me call it B vector. Okay, to make it easier, let me call this to be T matrix. And let me call this to be C vector. What else I'm going to use? X transpose X. So let me call this thing to be X transpose X. And let me call this thing to be X transpose X. Of course, the formula. It's not X transpose X inverse, let's say. The formula will be provided in Excel, of course. What you are supposed to do is you are supposed to write the T matrix in the correct way and C vector in the correct way and apply this one. So let us continue. Now I have named almost everything to be more convenient for us. So what I'll do is I'll start from the middle. The first thing I need is X transpose X whole inverse, and I think I have X transpose X whole inverse. What do I need to do? I need to multiply it by. I can start from anywhere. I'll multiply it by, let's say, from the left side, which is T matrix. So T matrix with X transpose X whole inverse, I put a matrix multiplication command outside. Visible? It's the T matrix multiplied by X transpose X whole inverse. Then another multiplied by the transpose of T matrix. And again, outside, put a matrix multiplication. Yes. Done? Yes. I cannot. If you can, come and do it. I don't know the way to zoom the address bar. No, the columns can be zoomed, but the address bar, I don't know the way. Then what to do next? Take the inverse of the whole thing. So outside this one, I put matrix inverse. Take the inverse of the whole thing. What to do next? multiply it by T beta hat minus C. So, comma, another command of matrix multiplication, T with, what do I know? What did I name? BV? Yeah, BV minus CV and I multiply these two outside. I'm done with this part. Again, pre-multiply it by the transpose of this last thing that I have, this thing. I copy it all the way up to this. Copy it and pre-multiply it by the transpose of this thing. And outside I put the matrix multiplication and close the bracket. Complete. So now if you look at the formula, it is the matrix multiplication of the transpose of T beta minus C into the matrix inverse of T times X transpose X whole inverse times the transpose of T into T beta minus C.
So you don't need to put the matrix inverse command between the X and the X expose.
Matrix inverse? No, there is this. Oh, yes. Where is it? No, I have to put. There is inverse here. This is the inverse I'm putting.
Yes.
It's not the I need to put 168 point something. I have to divide it by R. What is R? The number of rows of T matrix or the number of conditions we are testing in H naught. 1 divided by what? The MSE of the full model. Where is the MSE of the full model? I have it somewhere. Here is the MSE. 10 point something. What do I get? 15.85. Do you remember this number? 15.85. This is the square of 3.981313. The same we got in the last class for testing beta 2 equals 0 with the partial F test. So if I try to find the p-value, what do I get? For F test, the p-value is the upper tail area. So 1 minus F dot dist F distribution. I want this one, comma 1, comma, what's the denominator degree of freedom? 22, comma 0.00631, exactly the same that we got from the two methods that we discussed before, the t-test and the partial F-test. Why we did all that? Who can answer this question? Just showing it that they are equivalent, but it's not necessary that I ask you this question. I can ask you this question in exam, and this one cannot be done with t-test. This cannot be done with the partial F-test. This has to be done. The one I see now, this has to be done with what? With the generalized linear constraint test. So now let us try to test one more constraint, one more hypothesis, which actually does make sense. Now, what I did is I found beta 1 plus 10 times beta 2, and I got 1.9. Suppose this is after, I should not do this. This is after fitting. I observed that beta 1 plus beta 2 times 20 is 1.9. Suppose the scientist who is designing this study, he told me to do this before starting the hypothesis. That once you fit the hypothesis, you may get beta 1 plus 20 times beta 2 to be equal to 1.9. Suppose this is what I want to test. This is what I want to test. H naught beta 1 plus 20 times beta 2 equals 1.9. No other test can be used except for this one.
That's
For
to be
this
equal, it's greater or none to anything.
No, one-sided, no capacity of test. F test does not have the capacity to test one-sided.
The first one is the plus, right?
It is a plus.
Equal to.
Logically, what should be the final decision? You should be accepting H naught with a very high p-value. Because I just observed that beta 1 plus 20 times beta 2 is close to 1.9, is it? But again, in real life, it doesn't go this way that after you observe, you start testing. No, it comes the other way. Before the study, the constraints should come. So this is just to show you that I'm expecting a small value of F for this hypothesis and a high value of P value for this hypothesis, and see what I get when what will be the T. Anyone who wants to practice for T, raise your hand. Yes. 0, 1, 20. Just a one condition. These are not two conditions. So there will be only one row. 0, 1, 20 and C will be 1.9. You just have to change the row and everything is already done. 0, 1, 20 and C is 1.9. Look at the value of F. We were expecting it to be close to 0 and we got close to 0. Look at the P value. We were expecting it to be high and it is high. Why? Because the constraint seems true according to the data. According to the data, constraint seems true and B1 plus 20 B2 is actually equal to 1.9 something. So the data are favoring the constraint. Yes. Definition of condition, linear condition that we're testing.
Slopes, when you add them, should be equal to.
The constraint is that the sum of the first slope plus 20 times the second slope is 1.9. Just a condition, I can formulate hundreds of those conditions just for the practice of testing. What if I want to test that beta 1 plus 20 beta 2 is 900? Do you think the data will favor this? What do you expect from F? What do you expect from P value? Let's see. I just changed the number in C and you will see. So when I change this to 900, look, the F value is in millions and the P value is, again, it's not exactly 0. You will never get F value exactly 0 because the P value is the upper tail area. And for F distribution, the distribution starts from 0 all the way up to infinity. So no matter how big F it is, the upper tail area never becomes exactly 0. It is almost 0. So it is maybe 16, 17, 20 decimal points and then 0.0000, many zeros and then something. But Excel is rounding.
Sorry, what's the definition of P?
P what?
Definition of P.
The P value?
Yes.
This is the probability of getting a value of F this big if H naught is true. It cannot be 0. The P value for F test is something like this. This is F distribution. It starts with 0, goes all the way up to infinity, and this curve never touches the x-axis. Never touches the x-axis. It keeps getting closer and closer and closer and closer to the x-axis, but never touches the x-axis. The area never becomes exactly 0. Okay. Now, no matter how big your f is, our f was 5 million and something, very big, right? And p-value is the upper tail area, this area, the one I shaded.
So this is also applied on T and Z.
Of course, yes, but that's two-sided. This is applied on every distribution. When you look at the tails never touch the x-axis. They always keep getting closer and closer and closer and closer to the x-axis, but never touch it. That is why for z you always cover between, let's say, plus minus 3. Outside plus minus 3 you don't see it because the area is negligible, almost negligible. Yes, you can use the critical value approach also. The critical value, we found it last time, was 4 point something. So of course 5 million is more than 4 point something. The critical value was 3.44. So of course this big number is more than 3.44. Any questions up to this point? Yes.
Give us lift area.
Excel always gives you the left tail area, the less than area. If you want to convert it to greater than, you always have to do 1 minus. Inside the command, there is no argument that can make it upper tail area. Like in R, we have the way to make it upper tail area. There is an argument within the command, but in Excel, there is no. So you have to do it by using the concept of probability and by taking the complement of the event 1 minus. If you want the upper tail, do 1 minus. But in other programs, there is option of changing the lower tail to upper tail. Call it upper tail, and without doing 1 minus, it will give you the upper tail.
But the F does not have the F distribution does not have low tail.
It has the like we have 5. Let me change it to, let's say, 2. Now f value is 0.6621. Okay. Now we have the f distribution is from 0 to infinity, right? We are interested in the area from 0.6622 all the way up to infinity. We are not interested from 0 to 0.6621, but Excel will give you from 0 to 0.6621. Then we are taking 1 minus of that thing to get to the other side. Any other questions? No questions. In case of no questions, let me see what's next in the book. No, there are two main topics left in the book. We are done with 3.3, the hypothesis testing, all types of hypothesis testing. Now we go to the prediction. Yes. Yeah, the prediction. Now, exactly on the pattern that we discussed in chapter 2. Once the model is fitted, it can be used for two purposes. What are the two purposes? Estimate the mean of y when x is x naught, correct? Predict the value of y when x is x naught. These are the two things we did in chapter 2. Estimate the mean of y when x is x naught, predict the value of y when x is x naught, and we observed what? The point estimates are the same, but the interval estimates are the different. Now in chapter 3, what will happen? This will happen. No change. X will become a vector. That's it. There, x was a value, correct? Now it will become a vector. What type of vector? Let me tell you. Now suppose your data is like this. y1, y2, all the way up to yn, and your x matrix is something like this. 1, 1, all the way up to 1. You have x1, 1, 1, 2, 1n, x2, 1, 2, 2, 2n. Say you have two predictors. Now I give you a question that, let's say tomorrow, that person who fills the vending machine, he has to go and fill a vending machine that has number of cases equals 20 and the distance equals 100, let us say. Predict y or estimate the average of y. Same two things I can ask you. For this setting, either I ask you to predict y or estimate the mean of y. So I'm asking you to do the prediction or the estimation of mean response for this extra row, a new setting of X matrix, right? To do this, what will you do? Put it into the equation. You have the equation, you have this equation, correct? Y hat equals beta naught hat plus beta 1 hat x1, beta 2 hat x2. Put it into the equation and you get the point estimates. Any problems? No problems. Put x1 equals 20, x2 equals 100, and you get the y hat. And same is the mean of y, because the point estimates are, they are same. How can I do this in terms of matrices if I want? My fitted model is this. In matrices, my fitted model is that, right? Now, my X matrix is what? It is this. Correct? Now, if I want to do the prediction, I will do this y naught hat equals the new row of X, whatever it is, this one times beta hat. Put the new value of X into the model and get it done, right? Right? And this new X naught is what? It is this row, 1, 20, and 100. 1, 20, and 100. Why 1? To compensate beta naught hat. 20 to be multiplied with x1. 100 to be multiplied with x2. Now, according to the notations of matrices, when you define a vector, usually we don't define it as a row vector. Usually, if you write just a vector, that means a column vector. So the notation I'm going to give this x naught is just the notational method. Don't worry, it's not a concept. The notation I'm going to give this to the new row is x naught prime and not x naught, because I'm going to define x naught as a column, but I need it as a row. OK, so the notation I'm going to give this one is x naught prime equals 1, 20, and 100. So I'll put a prime here, so that the original x naught becomes this 1, 20, and 100. So that the name given to the vector is a column 1, but because I need the row and not as a column, so I'll take the transpose of that one. So let us try to do the prediction for, let us say, this setting. For this setting, the first thing I will do is I will define the new x naught prime. So the new x naught prime, you can also do it in the scalar, but the prediction interval, you cannot do it in the scalar. Let me define x naught prime. It is what? 1. And let me give it a name. X naught. I think I selected one extra column. X naught transpose. I gave it a name x naught transpose. So the fitted value against this one will be what? Y naught will be matrix multiplication. What do I multiply? X naught prime, x naught. Where is it? It's not appearing. Why it is not appearing? Did I give it a name? X. Here it is. I did not put 0. I put O. XOT with beta hat. Did I give the name beta hat? BV. Yes. So the predicted value is what? 36.0 something. I can do it manually by not going into the matrices also to confirm. This is beta naught 2.31 something plus beta 1 times 20 plus beta 2 times 100. And I expect the same answer, 36 point something. Yes.
Why not just X possibly as a column?
You want to enter X naught as a column vector?
Yes.
Then you'll have to put an extra transpose command here. X naught, if you enter it as a vector, then you'll have to take the transpose of it to multiply it to beta. You can do that, not an issue. Enter it as 1, 20, and 100. And then when you are finding Y naught hat, before multiplying it with beta hat, take the transpose of that. Any questions up to this point? In the next class, I will define the prediction interval and the confidence interval around this point estimate. Now, let's talk about the exam.